All right, in this video, we're going to talk about a second type of comparison test. This one's called the limit comparison test. And the regular one that we just talked about was more intuitive, and there really weren't a whole lot of predetermined things that you had to establish. This one, however, is a bit more mechanical, and that might be good, that might be bad, depending on the problem. But regardless, it's an option if you want to compare it to something, but let's say the inequality doesn't hold like it needs to for us to draw a conclusion, we can still proceed forward with possibly the limit comparison test. And so for this one, if series a sub n and b sub n are positive termed, okay, this is the one that's going to be given. This is the one that we're going to come up with to compare it to, okay? Then if this limit where we have a sub n over b sub n is one of these three things, then we can draw some conclusions. So if this limit right here, we'll do that in a different color, if this limit ends up equaling c, where c is bigger than 0, then both the original and the one that we started with both either converge or diverge, okay? If the limit equals 0 and the one that we came up with, the one that we're comparing it with, converges, then the original converges. And then finally, if that limit is equal to positive infinity and the one that we came up with diverges, then the original one given will also diverge. And so we'll go ahead and look at a couple examples, and you'll see how mechanical this can be. And hopefully it'll be a nice alternative to the other comparison test when it's not able to be used. All right, so as we take a look at this example, if we want to move forward determining convergence or divergence using the limit comparison test, we're going to have to pick something to compare it to. And much like the last test, it's all going to be about what's important. In the numerator, this square root of n is going to be dominant. In the denominator, if you were to multiply all that out, the n cubed is what would be dominant. So what I might start with is a square root of n over n cubed, which of course could be simplified down to 1 over n to the 5 halves. Okay, so that's going to be something that I'm going to use to compare it to. I know that this series converges by p series. All right, so we're going to keep that in the back of our mind as we move forward. Now, to set this limit up, the limit is n goes to positive infinity. We've got our original over the one we came up with, which would be 1 over n to the 5 halves. Okay? So to simplify this, I'm essentially just going to flip that around, and I will go ahead and distribute it into both of those. So that's going to be limit as n goes to positive infinity. This will be 2 times n to the 5 halves plus n cubed over the n plus 1 cubed minus 1. Okay, so now as we look at this limit as it goes to infinity, the dominant part would be n cubed, the dominant part would be n cubed, so really we're just looking at the ratio of leading coefficients, which would in fact equal 1. And since it equals 1, it falls into that category of being bigger than 0 and finite. Therefore, what this thing does is the same thing as this thing. So since this one converged, therefore our original has to converge by the limit comparison test. So therefore, the original converges by the LCT, limit comparison test. So again, it's much of the same in that you're going to compare it to something that you know, but the inequality didn't come into play here. And because of that, we're able to use the more mechanical approach of evaluating the limit and then just drawing a conclusion based upon what the result was. And then again, I've summarized, letting you know that we've established that this original series does converge by the limit comparison test. Okay, so for this one, we're going to go about it the same way. What should we compare it to? Well, the 1 in the numerator is going to be a 1, and this is dominant in the denominator. And so I would start off by comparing it to the series of 1 over n. Now, I could certainly put the 2 there if I wanted to, but what would happen is I would just pull the 1/2 out, and then this would still do the same thing by pulling the constant out. We know this being the harmonic would diverge. So if you put the 2 there, it's fine. If you don't put the 2 there, it's perfectly reasonable as well. So again, this thing we know diverges by harmonic. All right, so now for the limit. As n goes to positive infinity, the original over the one that we came up with. And much like the last one, I'll just kind of flip this guy around. That's going to be the limit as n goes to positive infinity of n over 2n plus natural log of n. And so you can see by evaluating, we would in fact get the infinity over infinity. So I would proceed forward with L'Hopital's rule. And in that numerator, we're going to get a 1. In the denominator, we're going to get a 2 plus 1 over n. At infinity, this guy goes off to 0, giving us a final answer of 1/2. Since that 1/2 is bigger than 0 and finite, we know that this guy then does the same thing as this guy right here. So since this diverged, we can say now the original diverges by the limit comparison test. So therefore, the original diverges by the limit comparison test, LCT. So again, as I've said before, it's going to be important to establish the comparison. In this particular case, no inequality is necessary. We don't have to worry about that. It's just going to now lead us into a limit, which hopefully you've gotten pretty good at over the last few months.